All right, let's see. So yeah, hey guys, I'm Jerry. I'm the head tutor for Signals Systems here. So I'm gonna just go ahead and get started with the exam 1 content. So y'all covered what is a signal, how do we manipulate them, how do we process them with systems, and those are all things that we're going to cover here for this first exam. So starting out, what is a signal? Typically, it's just some set of data that's going to depend on some other variable. So if we have a continuous time signal, it's going to be a function of a continuous variable. So f of t. Yeah, so if we have this nice sinusoid here, it's going to vary continuous over time. It's going to have a continuous domain. Whereas if we have a discrete time signal, we're going to have a signal that looks a little bit more chunky. Yeah, so it's going to have a lot more spikes. It's going to consist of mostly delta functions. Yeah, only delta functions at regularly spaced intervals. So say we have the spacing of integers. This would be sample 1, sample 2, sample 3, sample 4. But there's also different ways that we can represent discrete time signals, namely one of them being like a list, so it's just some list of numbers. Yeah, this could also be considered like a discrete time signal. Yeah, and we'll typically denote those with f of n with these little brackets. Right, so that's our definition of a signal for this class. We could go into more details if we're going to more into math, but we're engineering, so we're going to stick to this right here. So I'm going to define a few terms, because I'm going to say these, I like to say them a lot just when I'm speaking, so I'm just going to just refer to them periodically throughout the review, just so it makes sense. Also, let me just make sure I'm recording. Yeah, I am. Okay, great. So the support of a signal. So if we have some either like I'm going to say it's a continuous time signal, then like what I mean by the support of the signal is just all the t values that are non-zero. Yeah, I'm talking about the t values here. So yeah, so it's t such that f of x, so f of t is not equal to 0. Yeah, and I might denote this by this bold t. Yeah, this is just preliminaries right now before we get into the meat of things. So yeah, there is different properties our signals can have. One important one for this class is it being either periodic or aperiodic. So what do we mean by that? We have a function. If it's periodic, then there's going to be some number t, big T, the period, such that if we start at that time, it'll look like the same function. Yeah, it'll loop back around. So if we have if we start here and our function is a circle, we'll loop back around to the start again. That would be something that might be like 2 pi periodic. It's just we're advancing in time. A periodic signal in one dimension would be something like sinusoid. So notice that we get copies after the period. So let's say this is the period t. Yeah, we'll get copies at every integer multiple of t. Copies. Periodic copies. Great. So, and another thing that I'm going to talk about is something called piecewise behavior. So basically, if we have just some signal that's broken up into different types of behavior within different regions. So like say we had this nice like curvy thing, say we had this nice like wavy, and we got this straight line. Yeah, so notice that there's different behavior within different points in time, so t1, t2, t3, t4. So like one way we might denote this, I'm probably going to end up denoting sometime in this review, is with this piecewise function, this bracket thing, which just tells us, well, this acts as behavior 1 in the region from t is less than, oh, that should be less than t2, less than t1. Yeah, then we got the behavior that's f2, and this will be in from t to t3 to t2, and we got this third behavior here in this signal. Yeah, so f3 t, t3 t. Right. So yeah, this is just how I'm probably going to talk throughout the rest of this review. So I'm not sure if this is consistent with your professors, because this is kind of a combined review right here. But yeah, this is the one that makes sense to me. So that's what we're sticking with for right now. But anyway, so we have what a signal is. But great. So we often like to stretch and scale them. We like to be able to use our signals in more the ways than one. So how can we reuse information, basically? So we'll often do that by manipulating our signals. So if we have just some signal, we can shift it. Let me put it out like this. Okay. Yeah, so if we have this signal, then if I have, this is a time axis. So, right, we can shift them left and right. Oh, let me say this is f of t. And let's say that a is some positive number. I'm going to say it's probably like greater than 1. Yeah, but yeah, so we can move this left and right in time by delaying it. Let me take this. So if we have our signal, so if this one is f of t, then shifting it left, so it would go backwards in time. So this one would be f of t. Let me use a different color here. So this one would be f of t plus a. Yeah, so we're going backwards in time, so we're adding to this time variable. But if we are going forwards in time, so we're going to shift it to a right. Shift right is f of t minus a. Yeah. So to the right, we have a negative sign. To the left, we have a positive sign. Right. And we can also move them up and down by just adding a constant. So let's see. Yeah, so if we have our signal, yeah, so we're going to move this up and down. So if it's in the middle here, let's say that's 0. So if we go up, we're going to add a. And if we go down, we're going to subtract a. But yeah, I don't think that is necessary to illustrate that more. But we have, so we can stretch and scale these horizontally and vertically. So we can basically just mold them into whatever picture we want them to look like. Also, just to check, everything's working well on Discord, right? I don't know if anyone can hear me right now. Okay, just making sure. Yeah, so we got, so we can stretch and scale things horizontally. So this would be a stretch that looks like this one. Let me make this red, green, red, yeah. So this one would be f of at. So we're scaling our time variable up. It's going to get bigger, so everything's going to move faster, so things are going to shrink in time. It's going to get smaller horizontally. And we can also make them bigger by dividing our time variable. So this one would be f of 1 over a times t. Remember, we have a is just some positive number greater than 1 here. Yeah, for all of these illustrations. But yeah, and then we also are able to stretch and scale them vertically just by using standard multiplication. Yeah, so if we have our signal, then we can go up by, that should be same size, say that's the same size. Yeah, so that's f of at, and then shrinking it down, it's red, is going to be 1 over a f of t. And also notice that this this can also make our signal turn upside down if we have a negative number here. So keep that in mind. And yeah, so those are that's pretty much what we can do with just our signal itself. But if we throw in some useful signals that we'll see time and time again in this course, then we can actually do some pretty cool things with them. Wow, we can cut them off at one point. So basically, if we have, so I'm going to define the unit step function right now. So the u of t is, so it's 1 for everything on the right, so t is greater than 0, and it's 0 for t is less than 0. I mean, people have different definitions for the condition at 0, but for the most part, it doesn't matter. So this is the one I'm probably going to end up working with. So we got, so if we have some signal that looks like this nice exponential function, yeah, I'm going to draw this all dotted. Then if we multiply it by this unit step function, let's give this an axis, this is 0. So if we have the unit step function, then we're going to multiply it by this blue signal here. And notice that this gives us everything that's on the right of the x-axis, or of the y-axis. So this gives us just this exponential that is cut off at 0. So that's what I mean by we can cut things off. And we can also specify any kind of piecewise behavior that we were talking about just a second ago with this unit step function by just having like a sum of them. So like if we wanted to specify a certain region, we could have 2 different step functions. Yeah, this one's just a flipped and shifted version of the unit step. And this would give us something that looks kind of like this. It would just it would cut off the left and the right side now. Yeah, but this would be written as like a sum of 2 unit steps. So this would be like ut plus ut minus 1, or yeah, minus t, so plus a or something. Yeah, shift it to the, wait, no, we want to shift it to the right, so right, yeah. So yeah, and this would specify the behavior that's in this region from t is 0 to t is greater than 0 to t is a. Right. And I'm going to also define the delta function that we've talked about. So, and this lets us, this function is special because it lets us sample a specific value at any point in time. So, yeah, this is the working definition of the delta function right here. So, there's a lot of different definitions that people will give for this. Some people will say at 0 it's undefined. So they would write like an infinity symbol here. They might say it's undefined. They might say it's some limit of this like rectangle function, and that's all well and good. But I've never been able. I've always gotten away with just saying that it's the value 1 at t is equal to 0, and this tends to. No one's really going to get mad at you in engineering for using this definition of the delta function. Yeah, but anyway, this is the one that I'm going to work with here. So we have, this just lets us take a specific value of our function f at some point in time. So I'm going to draw my exponential function again. So this is 0. So if we have a delta function here, then we're going to, so I'm going to draw the delta function like that. I might also just draw it like spike, like just a line later on, but anyway, it's a spike here. So this would give us the value of this, yeah, exponential. Actually, let me not have it just be a plain decreasing exponential. Let me redraw this real quick. Yeah, let me say that this is exponential that's like, or this line. It's just, the point is that this is above 1. So this is a at 0. So this will give us, multiplying these two together, so this delta function times our function of t, f of t, this gives us a scaled version of this delta function. So this gives us a delta function with the same height as our original function. So we have delta t times f of a, f of 0, yeah, where we have 0 being the point that was sampled. So this is great. We can turn, so this will let us turn continuous time signals into discrete time signals, vice versa. It's great, but that's it. This is all we need to know for right now. Multiplying by a delta gives us a scaled delta. Right. Yeah. So we can manipulate signals, but this probably doesn't cover the full extent of things that we'll want to do with just any arbitrary piece of data that will be given. So we'll want to manipulate it in more complex ways, like turn like a picture of a cat into a monkey or something, or make our room turn on or something. But yeah, so yeah, this brings us to systems. So in general, a system is something that just turns one signal into another signal. We typically denote this output as y. And that's really all we can say about just an ordinary system right now. It's just a function that it turns a signal into another signal. But we can't actually know how it turns the signal into another. Right now, if we don't have any other information, then H is what we call a black box. So this black box is something that we don't know how to put things together. We don't know how to interpret the output in terms of the input. So we can almost think of this black box as just magic. One way I like to think of it is like if we gave a monkey a typewriter and we told him to write, what would he give out? Like we tell him, hey, write something, monkey, and then he goes, all right, he bangs on the keyboard. What do we get? Who knows? Who knows? What happens if we add two monkeys together? Like, well, we don't know. Yeah, so that's all I wanted to say about just a general system. I think a lot of people get confused whenever we start talking about like impulse responses and LTI. Like, what's the point of all of this? This is the point of it. We want to have things that change our signals in a way that is interpretable. We want to be able to figure out the output from the input, and in any combination of these systems of a certain class. Like right now, we can't do much. Yeah, so yeah, we'll typically design our systems with a few of these properties in mind, because they make things a lot easier on us in applications. So, right, so we have a few properties. So the first one that we should talk about is linearity. So I'm going to denote this mapping of one signal to another as just the function notation right now. So we have h is just some function, x of t. So we're mapping x of t. If I write this, this just means x of t is getting fed into this block h. Yeah, you can kind of look at this as y. Yeah, but so if a system is linear, then if we put in a sum of two different input signals, then we'll get the same thing in the output. We'll get the sum of outputs. So a x of t plus, I'm going to say b, what's another letter? Y. Okay. No, I'm not going to use that. I'm going to use f and g. F of t. Yeah, because I've told you already that y is the output. I'm going to stay consistent on that. So f of t and then g of t. Then we should get the sum of these two signals, the outputs of them in the output. So we should get a times h of f of t plus b times h of g of t. Now the other signal there. Yeah, we should be able to take out coefficients and add outputs. And then another property that's important for the class of systems that we're going to define is time invariance. So what this means is that if we have an input, so we have x of t, and we know that this one gives us y of t, then if we shift the input, so we have x of t minus tau for some tau, yeah, then this is going to give us, a shifted input is going to give us the same output, but it's going to be shifted by the same amount. So y of t minus tau. And this has to be true for all signals. Yeah, for all signals. For all x of t. So if there's a single x of t that doesn't satisfy this, then this isn't true. Yeah, once we have these two properties, then we're into this really interesting class of systems called LTI, yeah, linear time invariant. And the special thing about them is that they're this interpretable class of systems that we want. And we get there, we can predict the output from the input by the convolution of the impulse response. So yeah, so if a system is LTI, so H is LTI, then we'll be able to get the impulse response. So what is the impulse response? So that's just where we put in a delta function as our input, and then whatever you get out from that delta function, that's our impulse response. We're typically going to denote as h. Yeah, Yeah, so let's h of t. Then we can actually get the output of the system for any input that we put in. So x of t convolved with h of t is equal to y of t for any signal that we pass through. And this is huge when at first we were just looking at, well, we have the input and we have the output, but we don't actually know how we got the output from the input. That's the difference here. And oh yeah, also, was there a question before we move on? Well, I assume not. Well, yeah, so a few other properties that are really useful for us in practice are something called causality. So basically, we just want our output, y of t, it's going to depend only on, it's going to be some function of the x of t's that come before it. It's not going to depend on future samples of x of t. Yeah, so where t, let's write this as tau. Yeah, so it's just going to be a function of all the taus such that tau is less than t. So we have tau is less than t. So so basically, as an example, if we have y of t is equal to x of n minus 1, this is going to be causal, but if we have y of t, oh shoot, I was writing in t, this should be a t, yeah, y of t. So this one's causal because we have t minus 1 is always going to be less than t. So this system is causal, but this one is not, even though it looks pretty similar, t plus 1, because t plus 1 is a future value. So like if we picked a specific value of t, so y of 0, then y of 0 would depend on x of 1, which is bigger than 0. Yeah, 1 is bigger than 0. So this depends on future. So this one's causal, this one is not causal. And that's just one example, pretty simple example. We'll go into more, we'll do more computational problems towards the second half of this review. How I structure these is, the first part is just me going over the theory, and then we'll get into examples in the second half. So if our system has memory, then y of t is going to depend on other values than the present. So going back to our examples there, so we have, so what if we have x of t minus 1 plus x of t. So this system is going to have memory because it depends on t minus 1 and t, more than one value. But if we have y of t is equal to x of t minus 1, this also has memory because we're going to have to store this value, this t minus 1. This isn't the present value. But if we, so this one has memory, this one also has memory. Let me make more space. But if we have y of t is equal to x of t, then this one will not have memory, no memory. And this is because y of t only depends on the value at the present. So basically the index variable is t across any of the inputs. So basically, if we, this is another example of a system that has no memory. It's memoryless. Yeah, so the absolute value of it. Or if we added like 2x of t to the 8th power or whatever, like, so as long as we have the same time variable in each, then it has no memory. It's memoryless. And after that, we have stability. So this is helpful in guaranteeing that our system's not going to like blow up or anything. So this is a property that just says that if you can check it pretty easily by like applying the test. Like if we have x of t, so assume that x of t, the absolute value of it, is less than or equal to some max, I'm going to say m, then this should imply that, hopefully it does imply that y of t is also less than some other bound. So like it's going to be less than some number. This can be any number as long as it's finite. As long as it's not infinity, basically. Yeah. So like if we had, so a simple example real quick is if we have the system of, let's see, y of t is equal to x of t plus a of x of t minus 1. Let's see. That's, so notice that if this system is, notice that if this is bounded, so if we assume that this is true, x of t is less than m, then if we put absolute value signs over everything, x of t plus a x of t minus 1, this is an example, then notice that we can do this. We can turn it into inequalities. So the first step here is to break up this plus x of t, and this is called the Triangle Inequality. So a of x of t minus 1, and we get this upper bound. It's the absolute value of a sum is bounded above by the sum of absolute values. And then since x is less than m, then we have that's also bounded above by m, and then this is, can break up that a times x t minus 1 again. This is because the absolute value of two numbers is equal to the product of absolute values. Yeah, and let me just write the triangle inequality. And then we get it's bounded above by m plus a m. Yeah, so notice that this is a not finite. This is a finite number, so this is going to be stable. Yeah, so this is, so y is stable. This is not finite. It belongs to the real numbers. So y is stable. Yay. But yeah. So those are the different properties that we'll typically want out of our systems for the purposes of this class. So I'll be moving on to the next thing, where, because we'll want to measure our signals a lot of times. We'll want to be able to tell the difference. Like, we'll just want to be able to tell, well, this one has more or less energy than this one, or this one is bigger than the other one. We like to have a sense of scale whenever we're talking about different signals. So one way that we do that is by taking the energy of a signal. So if we have some signal x, then the energy of x is equal to the integral, the absolute of the squared absolute value of our signal over the entire domain. So this could be, so like if we have our x of t be finite support, so like so if we have a box that goes from a to b, then this integral would simplify down to like a to b. But if this b bound wasn't here, so it went to infinity, like a step function, then this would be bound from a to infinity, and so on. I think, yeah. But anyway, we just take the integral of the square absolute value. Yeah, remember this square and remember this absolute value. And yeah, this is what we'll use typically for aperiodic signals. So yeah, it's going to have energy as long as it decays to 0 at the ends. So like this sinc function, notice that it dies down to 0 at infinity. So we're going to take the energy of it, and this will come out to a finite value. Yeah, so this has finite energy. Energy x less than infinity. No, it's not equal to, less than infinity. But if we have this signal shifted up, so if we have the same sinc function, but it's shifted up by a value, that's a bad sinc function. Notice that this integral will always have some kind of area under it. So this energy is infinite. Yeah. This goes to infinity. So this would no longer be an energy signal. Yeah. So yeah, this energy is very sensitive to us shifting it up and down. But this is for things that are aperiodic. But what if we have signals that are periodic? Then what do we do then? Well, the most natural way to do that is to do something similar, but adjust it a bit. So what we do is we take the energy over a single period of our signal. So say we have a periodic signal. Then let's call this P of t. Then the power of the signal will be the limit as t approaches infinity 1 over t. So this is the formal definition of power. This is not typically what we'll use in practice because this definition can be kind of hard to work with. So this is the formal definition here. So this is P, T, the absolute value squared, don't forget the square. But if we have a periodic signal, so if P of t is equal to P of t plus big T, yeah, so we shift it over by T, big T, that's a really wavy T. Yeah, so then the power of the signal, so P, oh no, I didn't realize this PP, okay, then 1 over t of the integral over one period, so t over 2, and then minus t over 2. And this is true for any period of the signal P of t for dt. Right, so that's power. So if this is finite, so if this one is finite, then this would be what we call a power signal. If this energy, E of x, is finite, then it's what we call an energy signal. And no signal can be both an energy and a power signal. Yeah, that won't work. So so a few hacks that we get to do with convolution are as follows. So the delta function is kind of magic with this operation. I know that it kind of sucks whenever you're trying to really compute the convolution of arbitrary functions, but for the delta function, this is actually a really nice operation. So if we have a delta function convolved with any function x of t, then we know that the output is always going to be just the function that we're convolving with. This is to say that the delta function is the identity element. That's like saying 1 times any number, 1 times a is always a, or a plus 0 is always a. It's an identity element. So, and then it's also what we call associative. So we can switch around the order of wait, one other thing I need to cover on the identity property. So basically, if we have a shifted delta function, t minus a, then if we convolve it with some signal x, then we'll get x of t minus a. We basically replace the argument in this delta function we just put that argument into our x, and that's our output from that convolution. So maybe I should go over the definition of convolution real quick before we go further. So I mentioned that it kind of sucks to compute. So what I mean by that is we have x of t. If we have two signals x and h of t, then this is going to be the integral from negative infinity to infinity of x of tau times h of t minus tau d tau. So, and basically computing this involves that whole flip and shift process where we turn our variable, we turn our functions into a function of tau, we flip, and then we shift it along to find overlap. So that's all well and good. But yeah, convolution is something that isn't that bad here in this case, and really only this case. It's kind of intensive here, but a lot of our systems consist mainly of delta functions anyway, so yeah, I think this is worth covering. So we also know that if we have any signals that we're convolving, oh wait, let me use different letters. Really trying to avoid y. So if we have f of t and we convolve it with g of t, so if we do this one first and then convolve it with another thing, then this is the same as if we took our g of t, convolved it with h. So we did that one first, and then we convolved it again with the f signal. So you can switch around the order of convolution, it doesn't matter. And it's also something called commutative, so we can switch it like this also. So if we have our signal f of t and we convolve it with g of t, then this is g of t convolved with f of t. And this is significant if you look at the original definition of convolution. We can basically choose which one of these signals to flip and shift. It doesn't matter, but that's the important part of that. And then this is the distributive property, which is going to come in handy in a few examples that I'm going to pull up. So we get f of t. So we get f of t convolved with a sum. So we get g of t plus h of t. So we can distribute across. So we can get f of t involved with g of t plus f of t involved with h of t. And the usual properties with numbers apply also, so like FOIL, stuff like that. But yeah, that's really the most important parts of convolution. That's just defining it as a binary operation. But yeah, so like I said before, convolutions with deltas make copies. So actually I have like a demo to show you all real quick. Yeah, so if we have so in case it wasn't clear that we're going to be making copies of signals, this is something that I have here. Yeah. So if we have just some signal and we convolve it with an impulse, yeah, so what do we get? Well, we get the same function. Okay, that's not all that interesting. But what if we have shifted this impulse? Yeah, so notice that we get copies at each. Let me switch these. Yeah, but yeah, notice that we get copies at every single one of these delta functions. This is basically just a shifted over version of our original signal that we're convolving it with. So I think that's a helpful illustration. Oh shoot. Yeah, so that didn't get picked up on the recording, but anyway, I'll just go ahead and keep going. With OneNote. Let me pull that back up. Okay, yeah, so convolutions with deltas make copies. Another important identity to know is if we have a rectangle function, so just to define the rectangle real quick, rect t. So this is going to be standard unit rectangle, so defined by having area 1, so it's 0 outside of this region, t. The absolute value of t is less than 1/2, otherwise. And then another definition that you might see is the triangle function, so triangle t. It's going to be 1 minus t for t less than 1 but greater than 0. Let me move that over. I guess so. Okay. There, it moved. So, and then we get t plus 1, where t is greater than -1 and between 0. And then it's 0 outside of that. So if we were to draw that, then this would be that 1, 1/2, -1/2, and then this triangle gets. So this is peak is 1, and then this is going to be 1 at both the endpoints, -1. Right. So a useful identity is so if we have two rectangles together, convolving them gives us a triangle, standard unit triangle. Yeah, so this is going to come up later in one of the examples that I give. Yeah, and also some other formulas that are important for doing some of these energy problems, like are just some of the standard series that you get from calculus. Yeah, you'll probably see that if you have to take the energy of a discrete signal. So if we have the geometric series infinity n equals 1, 1 over 1 minus r, and where r is just some number from 0 to 1. And we also have the sum of finite number in the geometric series, so some finite number of terms, so Rn is equal to 1 minus r to the n. Wait, that's supposed to be big N. Big N, that's the number of terms, minus r, over 1 minus r. Okay, and then also the sum of the index variable, so k. So k is equal to, say 1, is equal to k plus 1 over 2. And the sum of k squared is equal to k times k plus 1 times 2k plus 1 over 6. And this is the same, k is equal to 1. Okay, and then, oh yeah, that's what I just went over. So text moving up. Oh, that's somehow worse. Okay. And so something that you won't typically see being taught in the course, I guess, but I think it's really helpful when we're doing these convolutions by hand, is a theorem that I found a little while ago. So it's basically, if we have a signal with a bounded support, so say this box which goes from, let me draw it like this, from A to B, and we have some other signal that also has a bounded support, so this one's from C to D, then the convolution of them is going to have the bounds, oh shoot, convolution's supposed to go over there, not right there. So if we convolve these two, then the bounds for the total thing is going to be A plus C and then B plus D, and then it's going to have some behavior in between there. I can't actually tell you what is going to be in there. It depends on the signal, but it's really helpful, this theorem here, to help check yourself when you're solving these problems. This can be, I found it to be very helpful, especially when you kind of have an idea about what the convolution is supposed to look like. So yeah, we've gone over just some of that. So yeah, time to talk about convolution. So consider this an example. So I'm going to, so I think a lot of people they spend too much time doing integrals and not enough time setting up the problem. So that's basically what this method is going to be. I try to claim that this is foolproof, but if someone runs into any problems and wants to prove me wrong, then go ahead. But let's see. So if we get a signal and we're trying to convolve it with some other one that looks crazy. So let's see. Let's convolve with this one. I'm going to have it look like a trapezoid here. So this is going to be 1 for t is less than from negative 1 to 0. And then this is 1 minus t. So my advice would to be not do this one directly. What we'll want to do is, oh, this is the unit rectangle, just to be clear. Yeah, so what we'll want to be doing is using the distributive property, because remember with convolution we need to find those bounds, and bounds are tricky in the most general case. So we'll want to be able to split this crazy function up into something that we see. I mean, I know it's not that crazy, but as an example. So we got from negative 1, so this is a rectangle. So plus this ramp, this triangle, 1, 1 minus t. So this one would be 1. So we want to convolve this with our box, our unit rectangle. So remember the distributive property. So we can actually take this one, convolve here, convolve with the box first, and then we can add those with the convolution with this ramp function, and then convolve it with the box. So yeah, if we remember that theorem that I was talking about, namely the one that says that if we have two rectangle function, two boxes, and we convolve them together, then this is going to be, let me parenthesize, parentheses, -1, maybe 1/2, 1/2, 1, 1, minus 2, 2, 1/2, 1/2, -1/2. Right, so this rectangle convolved with another rectangle, or I mean, it looks like a rectangle because it just looks like a rectangle but shifted over a bit. And if we combine that with that other theorem that talks about the support of the convolution, then we can actually figure out that this is going to be a triangle because we have two rectangles. So it's going to be a triangle with bounds from negative, so -1 minus 1/2, so a plus b, or a plus c, so 0. And then we have from 1/2, 1/2. So this would be 3/2, -3/2. And since these are both unit 1, yeah, so this is just going to be the standard unit triangle, but shifted over a bit. Great, so we have the easy part done, but we still have this one, and this convolution of this ramp function and this box. So what are we going to do here? We're going to take our signal and do our regular convolution method. So this is the one that I'm going to be using for demonstrating the method. So choose the one that you want to, so let me denote this f of t, and then this one g of t. Alright, so choose the signal that you want to flip and shift. Right. So of these two, which one's nicer looking? Well, I would say the one that's symmetric. So the one that you want to be moving around, I find it easiest to think in terms of the one that is symmetric. So I'm going to choose this box. This is the one that we're going to flip and shift. So the first step of this is to rename the important parts, or basically rename the important points of our flip and shift signal in terms of t. So what I mean by this is add t to both of these endpoints. So t plus 1/2 and t minus 1/2. I just added t. So this would be, this is what we're going to be moving around, basically. And then from there, you want to, let me add more space. Okay. Right, so from there, so we have our signal that is going to stay static, that ramp function. We don't need to rename any of the points of that one. That one's staying still. So this one's 1, and then, yeah, this is 1. But this box signal is going to be moving left and right. So we're going to draw the what I call the poses. So what I mean is just we'll have the box all the way to the left. We're going to draw another diagram where the box is slightly overlapping the right. Yeah. And then we're going to draw the next one where this box is completely overlapping the triangle. Yeah, just one needs to be encased in the other, basically. In general, if like these two lengths don't happen to be the same. And then need more space. Okay. Also, that should be a 1, not a 0. Yeah, and then we get signal, draw, and then the one that's overlapping slightly to the right, and then the one that is completely to the right. Yeah, so the first step is drawing these poses, I guess. They're posing for a picture. Yeah, how do you arrange them together? So let's see. And now from there, we need to write in these bounds, these t values for each one of these diagrams where we have shifted the rectangle. So this is t minus 1/2, t plus 1/2. So this one's t minus 1/2, t plus 1/2, t minus 1/2. This one's t plus 1/2, t minus 1/2, t plus 1/2. And then this one's t minus 1/2, t plus 1/2. Right. So we have all of our points named. So basically, all we need to figure out now is the bounds, and then from there, the integral should be pretty simple. You'll basically be doing the same integral, just be replacing the bounds with different things. So we get this one. So notice that both of these endpoints are to the left of this y-axis, so this 0. So we have both t minus 1/2 and t plus 1/2. These are both less than 0. So this is going to give us, so both of these inequalities will give us, so this one gives us t is less than 1/2, and then this one gives us t is less than negative 1/2. So, right, so we get two bounds here. So what we need to do is take the intersection of them. So we need to take the t values that satisfy both of these conditions. So this would give us, notice that this one is a smaller region, so this is going to be the one for case 1. T is less than negative 1/2. And then from there, we need to derive the bounds for the rest of them. So I'm going to do a similar process. So t minus 1/2 is less than 0. Again, it's to the left of this important point 0. T less than 0. And then notice that this one, t plus 1/2, is to the right. So this is actually bounded both above and below by 0 and 1, because it's in between the support. It's in the middle of the support for the triangle, the ramp. So this is t plus 1/2 is less than 1 and is less than 0. So solving out, this gives us t is less than 1/2, and this gives us t is less than 1/2 and minus 1/2. So again, we take the intersection. So notice that this region is bigger than, or this region is smaller than this one. Yeah, just because it has that lower bound. So we have case 2 is t is less than 1/2, and then 1/2. And then from there, we do this one. So notice that these two lengths are exactly equal. So we can write this as t minus 1/2. Notice that this one's exactly at 0, so equal to 0. And this right endpoint, t plus 1/2 is equal to 1. So both of these will give us t is equal to 1/2. So this is case 3. 3. T is equal to 1/2. Alright, second to last case, the last one's easy, so t minus 1/2 is to the handwriting's getting gross. 1 t, wait, that was it's minus, not equals. T minus 1/2. Notice that it's both bounded above and below by the left and right of this triangle, so it's 1, 0, and then t plus 1/2 is greater than 1. Greater than 1. So, yeah, solving the 1/2 less than t less than 3 over 2. And then this one is t is greater than 1/2. So intersection, then this one is going to be this one. So case 3, or case 4, 4. T is less than 3 over 2, 1/2. And then this one is going to be, if we follow a similar process, we're going to find t is greater than 3 over 2. And please chime in if it's not clear why. Yeah, so we got all that. And so we have a bunch of cases here. So what do we do now? We need to figure out all of the integrals now. So we just need to write the integrals, and then from there we will basically have our solution then. So from there, so just as a review, we took our flipped and shift signal, we renamed the points in terms of t, and then we drew our poses, and then from there we derived our bounds. And this gives us these different cases. So all we need to do now is do the convolution integral. So notice in this, we only need to do the integral for, oh shoot, why is this up? We only need to do the integral for the ones where there's overlap. So notice that these two signals don't overlap in this first case or this second case. So we already know that this integral is going to evaluate to 0. The convolution integral is going to evaluate to 0. So we already know that outside of these within these bounds, then it's 0. So now what about inside? So we got to do a bit more work. So notice that this only overlaps from 0 to t plus 1/2. We're only taking integrals over regions where there's overlap. Not here, because there's no overlap. Not here, there's no overlap there, but in the middle. So the bounds of the integral are actually going to be from the lower bound of this overlap, so 0, and then t plus 1/2. So this is integral from 0 to t plus 1/2. And this is, we just need to write the behavior now. So this one was, so our g of t was, so I said that g of t was the one that was shifting, right? So, so I'm going to write f of t is the ramp function. So f of t is 1 minus t. And notice that our shifting function is actually just 1. So times 1 is equal to, oh, wait, that should have been a tau. Tau, because we're doing convolution integral, times 1 d tau. Right. So now, when we do this integral, we should get something that looks like this: 1/2 minus t plus 1/2 over 2, this one squared. And yeah, we'll derive similar integrals for the rest of them. Typically, these behaviors aren't going to be changing between the different cases, as long as you did this thing where you break up the signal into its different behavior, the different regions of behavior, like we did in the first step. So I'm just going to write the bounds of this overlap here. So notice that there's overlap for everything, so we can just write from 0 to 1 over here. We don't need to use the t bounds because they're just equal to 0 and 1. Like, the integral would come out to the same thing even no matter which one you used. But so 0 and 1. So this is the same behavior inside, times 1 d tau is equal to, so I have that this comes out to 1/2. And then this one, so we get a similar integral. Notice that the overlap is here on the right now. So it's bounded below by this t minus 1/2 and above by 1. So let's write that, t minus 1/2 and 1. So same behavior, times 1 d tau is equal to, let's see what I write, 1 minus 1/2 minus t minus 1/2. I didn't really simplify these, but t minus 1/2 squared over 2. Yeah, so there's going to be some polynomial. And then we already have the last one done since there was no overlap. So yeah, basically that's our function. So we can write our final output, y of t, is equal to, so y of t being ft convolved with g of t, and this one is equal to this piecewise function, where it's all of these different behaviors. I'm just basically going to copy and paste all of this, and whoever's reading it can decipher. But yeah, if we want to look at a picture, no, that's not copying and pasting. Yeah, so that's our piecewise function. That's not how you write it formally, but you'd put the t bounds on the right. But yeah, for the sake of here, this is faster. Great. So that's our output. So just to show you what this looks like, so it doesn't seem like it's coming out of nowhere, I'm going to pull up the same demo again, where we convolve it with the ramp. Let me go to Discord, and then change windows. Right. Oh shoot, where's my demo? There it is. Right, so if we have our ramp function that we had, sawtooth, and this one, and drag this over. Yeah, so this one convolved with our unit box. It's going to look like this. So you're going to see the overlapped region in purple, and then the new convolution, the convolved signal, in black. So notice that from t is less than 1/2, so we have t is equal to negative 0.5. The signal 0. But as soon as we come into contact with our function that we're leaving still, we're going to get some overlap. So notice that there's this kind of polynomial behavior that's coming down, and then we get a max when we get t is equal to 1/2, because yeah, and then it'll look like that when things are all said and done. So yeah, just if you want to check my work by plugging it into a calculator, I would appreciate it. But yeah, this is my method of doing convolution. And one way that I like to check myself at the end of everything is to make sure that the bounds are, like the length of our convolution is correct. So we have, so this 1, 1/2, it should be a signal from -1/2 to 3/2. That's its support. And if we look at our piecewise thing, notice that it's true. So it's only non-zero in case 2, 3, and 4. So yeah, that's the method here. So, and if we remember, I defined this problem where we're using the distributive law to do this convolution of this more complex signal. So let me go ahead and draw out our final signal that we got from this one. So it looks kind of like this shark fin. Yeah. And then it's going to be shifted over a bit. Yeah. 1/2. 1/2, and then 3/2. -1/2. Cool. So basically from there, you just add up both of these signals pointwise. So if I were to give you this, let's see, this adding is difficult. But anyway, I think that this has been illustrative. Does anyone have any concerns, questions? I know I've gone a bit fast, but yeah, so if not, we'll go ahead and just do more examples. I'll probably cover an energy problem, maybe one with system properties, but basically this is what you're going to see on your exam. Just you're probably going to be asked to convolve some signals, maybe take an energy, or maybe do system properties. But yeah, this is pretty much going to be on your exam, convolution. I can almost guarantee it. But yeah, if there's not any questions, I'll go ahead and just do another example. So right, so I'm going to go ahead and do a convolution of a discrete signal right now. So let's say we have a signal, let me zoom in. Let me convolve this. Let's give it 4 stalks, and this is going to be from 0, 1, 2, 3, and then this one is 1. Actually, can anyone chime in and tell me if your professor has talked about discrete signals? That might simplify things a bit. Some professors like to put that at the end of the course, some in the beginning, but just to be sure. Is this something that's wanted to be covered right now? And be convolving 2 discrete signals. Okay, great. So yeah, so let's go ahead and cover this one since it's one of the professors. Yeah, but if we have this rectangle basically in discrete time, I like rectangles, so should you. And then let's convolve it with this exponential function. So it's going to come down, come down, come down, come down. This is going to be defined by h of t, or not h of t, h of n is equal to 1/2 to the n times u of n. Yeah, remember that the unit step function looks very similar in discrete time. I don't know if I went over it. Everything that you see in continuous time is basically going to look very similar to discrete time. It's just, instead of integrals, you'll see sums, and instead of real numbers, you'll see integers. But anyway, this is just 1 for x is equal to 1, 2, and 3. For n is equal to 0 through 3. Right. Oh, shoot. Let me go ahead and take it back. Thanks. Change window. Yeah. So yeah, I'm going to be convolving these two signals. So let's call this x of n, and this is 1 for 1 is equal to, for n is equal to 0 through 3, and then 0. So how do we do discrete convolution? So this one tends to be a little simpler, but it's still might be a bit troubling. It's basically you just, a lot of times you can just write the sum. So x of n involved with h of n is equal to the sum of x of, I'm going to say m, and times h of n minus m from infinity to infinity. So m is equal to negative infinity. Right, so, but notice that this signal is what we call causal. So basically everything to the right, everything is to the right of the x, or of the y-axis. Like there's nothing on the left. So actually this tells us that we can cut off the right part of our sum here. So this is going to be from m is equal to 0 to infinity. Wait, let me just switch the order of these. I think that would be easiest. Remember to always convolve by the one that is, always flip and shift the one that is least cumbersome. Yeah, so let's see, I'm going to leave this exponential in place basically. So we get this sum from 1/2 to n. And since we already cut off the left part of the sum, then basically we can drop the un. So it just becomes 1/2 to the n. And then we still need to write down x of n. But notice that x of m is only non-zero for, wait, hold on. Oh yeah, I just renamed them. So regardless, so this was un. So this one was x of n. This exponential, move it over. And then we have our, basically a rectangle. And then, so this one's h of n minus m. And we kind of need to do a similar game to like the continuous time. Notice that we want to be able to cut off the top end of this sum at some point. So how are we going to do that? We're going to play the same game. We're going to take our signal and we're going to run it across and then figure out the bounds. So we get, let's see, 1, 2, 3, 4, evolve on. So remember to flip and shift our x of n, or h of n, the one that's being moved around. So let's rename m plus 1. This one's actually m plus 1, m plus 2, m plus 3. But actually, wait. We were supposed to shift, or we were supposed to flip it first. This is remember to flip it. So we're gonna actually write this m minus 1, m minus 2, m minus 3. So this is the flipped version of our x. And then we're going to convolve it with our exponential. I know it's not continuous, but I'm just going to draw that. It's easier. So how is that? How are these going to interact? So let me draw those. But anyway, so draw the poses. So notice that this one has a unbounded support at infinity. So we're actually going to only get 3 poses now, instead of getting the 5 like we did before. So we have where it's all the way overlapped on the left, and then we have it's somewhat overlapped. And then this is where everything is completely overlapped. Oh, that should be yeah. So let's see how are we going to do this. So let's see, m minus 3, m minus 3, m minus 3, m. And notice that this only has one boundary point at 0. So, right, so let's see. Let's derive our bounds. So we need m minus 3 is less than 0 and m less than 0. So take the intersection. So this would give us m is less than 0. So this would give us, so now we need to derive this bound. So m minus 3 is less than 0, and m is less than, yeah, this one is greater than 0. So now we need to take the intersection of m plus, so m is less than 3 and 0. And then we need to find this one, which is going to be m is greater than 3 by a similar process. So yeah, those are our 3 cases. So let's go ahead and find the sum of these. So let's go ahead and write out the summation again. Sum 1 minus half n. So notice that there's no overlap in this first case. So for m is less than 0, then the summation of x, so x n h n minus m, this should be m, is equal to 0 for m is less than 0. And now we actually have overlap here now. So, but notice that the behavior here is still 1, like we did before. So let's just go ahead and write out the function. So I like to avoid trying to write n minus m in my sum as much as possible. So that's why we got a box here. 1/2 n is equal to, so from where is there overlap? So from m to 0, because there's only overlap here and not over here. So this one is from m, wait, hold on. I should have written this as n. Yeah, that was my advice. Use the same variable as we're using for our domain. So, but yeah, we can work with this, I guess. This should also be m. This should be m. Right. So this goes from 0 to n. Let me what this is. N. Okay, and then sum from n. Remember that geometric sum. So this one will be 1 minus 1/2 to the n over 1 minus 1/2. And then if you do some algebra, you can probably simplify it a little bit more. But I'm going to go ahead and skip to this one. So where is there overlap here in this one? So there's actually only overlap in this region from between m and m minus 3. So let's write that as n from n to n minus 3 of m is equal to 0, m is equal to 0, 1, 1/2, m. Okay, and then we can split up this sum into something that looks more like the geometric series. Like if we put in sum from n, m is equal to 0, because we want zeros at the start of our geometric series, m plus, so actually we're subtracting because, so we subtract out the sum that is not overlapping, basically. So everything to the left of this non-overlapped region. So that would be from n to m is equal to 0 to n minus 3, 1/2. That should be 1/2. Right, so now we just need to use that geometric series formula again. N over 1/2 minus 1 minus 1/2 n minus 3. And then you should probably do a bit more algebra to get it into one term, but y'all know how to do algebra, right? I do kind of sometimes. But yeah, so this basically gives us our signal for this convolution. Yeah, so we have our three cases here. Yeah, so m is less than 0, m is less than 3, less than 0. Then this one goes from m is greater than 3. Wait, why am I writing m? It should be n. 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 n is great. n greater than 3. Cool. So that's convolution of a discrete signal. Any mistakes, questions? I'm bad at algebra. But yeah, that's how we do it. For one thing I wanted to show with this one is that the same process works for a signal with an unbounded domain. So this one goes off to infinity. But in that case, it just reduces the number of cases, the poses that we'll draw. So yeah, it works for continuous and discrete signals. And yeah, from here, let's see. Let's go over a periodicity question real quick, because I don't think that I covered this one. Yeah, so let's see. So if we have a sum of periodic, so if we have like, so the question here is to take our signal here, x of t, is equal to sine 3t, or sine 3 pi t, plus sine cosine of 6 pi t. So how do we get the period here? So the sum of two periodic signals is also going to be periodic. So t, and this is going to be gotten by, so if this is x1 and x2, and they both have t1 and t2 period respectively, then the period here is going to be the least common multiple of t1 and t2. So for here, so the period of this one is going to be what, like 3? What one? Let's see. 3 pi t. Let's see. My algebra is escaping me. Let's just say it's 3. No, I think it's 1/3. It's 1/3. 2 pi 1. I forgot how to do this one specifically, actually. But anyway, let's call this one 1/3, and then this one is 1/6. So the least common multiple of these two. Actually, wait, this was a bad example. Let me just go ahead and go over to my graphing calculator, check the period, because I should know this, but I forgot. Let me see Desmos. Sine 3 pi t 3 pi x. Right, so this one has a period of 2/3. T1 is equal to 2/3. Then T2 is equal to I think 1/3. 1/3. So now the least common multiple of these two is going to be 1/3. Wait, the least common multiple. No, it's going to be 2/3. Because notice that T1 is equal to 2 times T2. Yeah, so that's our period for this sum of sinusoids here. Let's go ahead and do another example. So the rules get changed around a little bit for discrete time signals. So if we have, let's see, x of n is equal to cosine 2 of n. So if you're looking at this right now, well, it's cosine. It should be periodic, right? No, actually, this is not going to be periodic. And that's because we need to be able to write our frequency. So let's define the frequency to be 1/t. We need to be able to write this as some rational number. So it needs to be rational. So what that means is it's going to be some numbers a and b, where A and B are integers. And basically this is just going to be, and you can see that this period is not going to be, this frequency is not going to be rational. It's not going to be a rational number. It's not going to be in the form A over B. So, and you can see this by taking out 2 pi. So this would give us a frequency of 1/pi times n. Yeah, take out the 2 pi, then you get f. And then notice that our frequency f is equal to 1 over pi, and pi is not a rational number. Yeah, so we can't say that this is periodic. Yeah, so this is the case where it's a discrete time signal. But so a question now is if this signal will be periodic, sine of 4 pi n. So we need to factor it out into its canonical form, I guess. So we take out 2 pi from, we factor out a 2 pi in that argument. 2 pi times 2 times n. Yeah, so, and this gives us our frequency. And notice that this is 2, which is a rational number. We can write it as 2 over 1, so it is rational. So therefore, x is periodic. And in this last one, which looked very similar, it just didn't have this pi in there. This one is not periodic, so x is not periodic. Yeah, so that's what we got there. That's basically what I wanted to talk about with periodicity. We're going to, you might see a question about that, and this one formula is pretty helpful when you have sums, and sums of periodic functions. And these rules are important to know in discrete time. Yeah, this doesn't hold in continuous time. Like cosine of 2t is always going to be periodic. And same with cosine 2 pi t. These are both periodic. But the rules change a bit when we're in discrete time. This is one of the few differences between the two domains. Yeah, but other than that, let's see. What can we do now? I guess I haven't done any examples over energy. So I guess if we want to do a quick example here real quick of energy, let me just go ahead and snatch, and then make a new page. So I'm going to compute the energy of this exponential signal. So E of x. Yeah, so what is this? So then, since this is a discrete signal, so we're going to write the sum from negative infinity to infinity of n, infinity to infinity of x of n, the absolute value squared of x of n. Don't forget the absolute value and the squared. And then we're going to get, so notice that there's nothing below n is equal to 0, so we can go ahead and cut off that bottom part of the sum. So we get x of n. I'm going to go ahead and write out our function. So 1/2 n squared. So this is 1/2 2n. Yeah, because the square of a absolute value is always going to be the square of the argument. So like this comes from like x dot x squared. Yeah, wait, hold on. Yeah, so this one, absolute value, product of absolute values is equal to the square of absolute square of x And then, so we can take the sum now. N is equal to 0. So I'm going to go ahead and do a thing where I take the positive. So I'm only going to take the even numbers. So I'm going to write this as, so I'm going to do a substitution here. So m is equal to, I'm just basically re-indexing the sum to make it look like our original geometric series. Because for the exponential types, they're going to be helpful. Yeah. So this is just going to give us the 1 minus 1/2. Yeah. And this will come out to 1/2. No, wait, this comes out to 2. Wait, yeah, 1/2. 2, yes. That comes out to 2. Yeah, so that's the energy of this signal right here. So this is finite. So is this an energy or a power signal? So since this energy is a number 2, it's not infinity, then we can say that x of n is a energy signal. So another question that they could ask is x of n a power signal? What is the power of x of n? So the energy signals and power signals, basically if you have finite energy, so let me write, if x is an energy signal, then we have the power of x is equal to 0. So, and also, if we have some other function, so y, and if this one is a power signal, then we have the energy is going to be infinite. Right. So basically, energy and power signals are going to be a disjoint set. Like, they're not going to have, so there's no overlap between energy and power signals. They can't be both. There's nothing in between here. So yeah, that's what I wanted to say about that one. Yeah, so it's like 7:02 now. Let's see, that kind of brings us to the end of our time here. But is there any other concerns real quick before we go? Oh, hey, yeah. Uh-huh. So 2u of infinity? Is that what you're asking about? Like this step function at infinity? Minus 3u of t minus 1? Right. Yeah, okay, so like, whenever we write down infinities, we kind of get a bit hand-wavy here and there, but technically this is supposed to be written as the limit as, like, say, t approaches infinity of u of t. But what was u of t again? So let's go back to the definition. So it's 1 for everything greater than 0. So this limit actually is going to be 1. So 2 times, I mean, if we factor out this 2, so 2 times the limit of u of t t approaches infinity is actually going to give us the number 1. So 3ut minus 1. These are equivalent, I guess. Let me clean that up. 3 minus 3, oh wait, 2 minus 3 ut minus 1. Does that answer your question? Okay. That's no problem. So, yeah, definitely. Yeah, we have the t less than 0. Yeah, good questions. Good questions. But yeah, if y'all don't have any questions immediately, I guess I have some time tomorrow morning if y'all want to message me. My inbox is open, I guess. I don't necessarily have any time to take anyone for individual tutoring right now, but yeah, if y'all have any, what's up? What's up? Oh yeah. So we'll be posting the recorded review pretty soon. Yeah, everything is recorded. So yeah, we'll be getting that. I don't have the call recorded, but I think that we should be able to figure out from context. But yeah, it is recorded. Yeah, it'll be uploaded onto the IEEE YouTube page. Yeah, same page as the stream was supposed to be. Any other questions? Yeah, so if there's anything else, yeah, thanks for being here. Thanks for participating. I appreciate it. Yeah. Let's see. I don't really have anything else to plug right now besides my papers. I don't know. But yeah, I'll catch you around. All right. See ya. No problem.